Let's go through an example of calculating a triple integral using spherical coordinates. Now the problem is to compute the volume of a ball of radius a. Now in rectangular coordinates, b sub a is given by x squared plus y squared plus z squared is less than or equal to a squared. So the boundary surface is this sphere of radius a that we see here. And we want to compute the volume of everything that's inside that sphere. Now the problem doesn't explicitly ask for spherical coordinates, but as we'll see, the spherical coordinate system is definitely best suited for this computation. Okay, and just like in all the examples that we do, we always choose the coordinate system that makes the computation the simplest. Okay, so let's understand how these spherical coordinates work in this case. So we have rho, phi, and theta. Now this equation, or this inequality, can be rewritten as rho squared is less than or equal to a squared, because rho squared is x squared plus y squared plus z squared. So that means our rho bounds are really going from the origin, which is rho equals 0, out to the boundary, which is rho equals a. So rho goes from 0 to a. Now our bounds for phi and for theta come from thinking about in what directions from the origin do we have points. And in this case, because it's a spherical region centered at the origin in R3, we have angles theta going all the way from 0 all the way around to 2 pi, and our phi angles go from the positive z-axis at phi equals 0 all the way down to phi equals pi down here. Now we don't need to go past pi because we can just access that with a different value of theta. So our phi bounds are from 0 to pi, and our theta bounds are from 0 to 2 pi. So now we recognize that the ball of radius a is actually, in spherical coordinates, is sort of the equivalent to a box in rectangular coordinates, in that the bounds for the three coordinates are all constant. All right, so that's definitely a good thing. That's going to make things much simpler. So we have 0 to 2 pi, 0 to pi, and then our rho bounds are 0 to a. Now the only thing we have left to do is convert dv into spherical coordinates, and dv is equal to rho squared sine phi times d rho d phi d theta. Okay, so to compute the volume, of course, we integrate 1 dv, and so now we integrate 1 times rho squared sine phi d rho d phi d theta. So now we've written our triple integral, which right here is coordinate free, in terms of the spherical coordinate system. And at this point, it really doesn't matter that these are rhos and phis and thetas. The calculus is exactly the same as if they are x's and y's and z's. All right, now because we have a product of functions and of the different coordinates and constant bounds, I can split this triple integral up as the product of 3 single variable integrals. So I have the integral from 0 to 2 pi of d theta times the integral from 0 to pi of sine of phi d phi, and the integral from 0 to a of rho squared d rho. Alright, so we just compute each one of these separately. So this is just 2 pi. The integral from 0 to pi of sine of phi is equal to 2. You can sort of verify that on your own if you don't take my word for it. And then left here we just have this simple integral in terms of rho, which is the antiderivative is rho cubed over 3. And we're going to evaluate from 0 to a. Alright, so we have 4 pi and then times a cubed over 3 and minus 0 cubed over 3. So in the end we have 4 pi a cubed over 3. So the volume of b sub a is equal to 4 pi times A is really this radius of the ball, so 4 pi times the radius cubed over 3, right? And that sort of checks out, right? That's exactly what we expected this formula to be, but now we've actually verified or derived this formula for ourselves. Now you might ask, was using spherical coordinates worth it here? And to understand that, I think it's best to just write out what this integral would be in rectangular coordinates. So in rectangular coordinates, the bounds get much more complicated for this ball. So just to write them out, we get minus a to a for the x bounds, minus the square root of a squared minus x squared, and then plus the square root of a squared minus x squared for the y bounds, and then minus the square root of a squared minus x squared minus y squared, and then positive that for the z bounds. Now we just integrate 1, and then we're integrating dz, dy, dx. So the z bounds come from this inequality solving for z, and then the y bounds come from setting z equals 0 and solving for y. And then the x bounds are from negative a to a. So what we notice here is that the function is simpler than the function, the integrand in spherical coordinates. On the other hand, we can see that this integrand didn't really cause any big problems. It was pretty easy to integrate. So there really isn't a huge difference between the integrands here. But as you can see here, the bounds in spherical coordinates are all constants, while the bounds in rectangular coordinates are pretty complicated. And so that would lead this computation to be significantly more complicated than the one we did here. And that just demonstrates to us that spherical coordinates was a good choice of coordinate systems to attack this problem, which didn't really specify which coordinate system that we had to use. So this is an example of using spherical coordinates to compute a triple integral because it's the expedient thing to do. And we verified that the formula for the volume inside of a sphere is 4 pi over 3 times the radius cubed.